Imagine you have a graph, right? A graph indicating the velocity of a rocket, a graph indicating the growth of your revenue throughout the year, a graph indicating the quantity of some material in a construction site over a period of time. Just any graph that can mean anything, and this is the beauty of mathematics. If you understand the language, you can perceive it anywhere, everywhere, at any time. So imagine you have this graph, right? It looks like this, just for the sake of an example. Imagine you have point P here at, let's say, A. This is point P. At A, this is f of A. That point, right? And let's say you want to find the slope of a tangent line at that point. Now, why would you want to do that? Well, the interesting thing about this is that the slope of a tangent line, the slope of a tangent line at a given point means the instantaneous rate of change of it. So, like we said, this graph can mean anything: the velocity of a rocket, the growth of revenue, the total quantity of a material. It can mean anything. The speed at how a shark swims in the Arctic Pole. Anything. It can mean anything. So let's say you have this graph, right? And you want to find the tangent line. Now, what a tangent line is, and let me just erase this. This is a tangent line. Now, tangent lines are useful because they visually tell you where the point is gonna, direct itself to, oscillate. So as you can see, if we're using this graph, this tangent line, we can see that it's pointing that the point is going upwards. Of course, we can see that the point is not going that direction because we see the graph here. But I mean, if you don't have anything here, that tells you. Imagine you don't have on this side. That tangent line, tangent line tells you that the point is gonna be positive. Of course, it's not gonna be that direction, but it's still gonna be positive. And like, if we're using an example of, let's say, business, if this is the graph of your growth, and this is the last part of your interval, this is good. This is how you are gonna close the year, let's say. So you can show this to your boss and say, hey, look, we expect a positive value, the starting of the next year. But of course, nothing is pink color. That's an expression in Spanish. But basically what I'm trying to say is that nothing is as positive and as optimistic as we think. Therefore, we use math to avoid to reduce the margin of error in the future. So let's say we can see, forget the example I just gave, and let's say we can see the rest of the graph, right? So we want to know the slope of that tangent line at that point. So let's say we have another point here. Let's say that point is Q, and let's say that's an X, and that point is Q, X, f of X, and this is P, A, sorry, that's ugly, and that point and point A is A, f of A, right? The secant line, this is a secant line. The slope between 2 points, which is basically the same as the definition of a slope. And as you remember or think, the slope is the rate at which a function changes. No, well, it's the rate at which a variable changes with respect of another. So a variable, this is a variable, changes with respect of another, B. So of how variable A changes with respect of B. That's also how the secant line visualize the change. So as you can see, let's say we use the same example here of the business. If you draw behavior A no, sorry, variable A and variable B, and you draw a secant line, or also known as the slope, you will see that it's a negative trend, which is not good news. Or maybe it is. Maybe this is the graph of the amount of bacteria in a patient, or the amount of pollution in a certain area, in an urban area, which, I mean, you want to aim to negative instances, unless you're trying to kill people. If we look at this, let's draw the secant line. So the secant line between P and Q, right? So the slope of the secant line can be, let me just draw this. The slope of the secant line is basically the equation of any slope, which is g2 minus g1 x2 minus a1. So as we said, the slope is the rate at which a variable changes with respect of another, which has as so in general use, you want to see how x1 changes to respect of x2, or g1 changes in respect of g2. So in this case, the slope of that secant line, so the slope of the secant line P and Q, is f of x, right? Yeah. This is basically y, but I mean, I'm just putting it more formally. So if you might have seen a pattern here already. If you see, if we put Q closer and closer to P, the secant line gets closer and closer to the slope of the tangent line of P. You see that? So let's say, we are getting closer and closer and closer. You see how it's approximating the slope of the tangent line of P? We get it even more closer. It's almost identical, right? Just by a few centimeters in this case. So this tells you something. As the point Q approaches the point P, which is very, very close to P. So our goal here is to know the slope of a tangent line of P. Why? Because the slope of a tangent line at a point gives you the rate of change at that point. So you don't depend on other points. You just know what happened in that specific point. You don't need to take another point to see your change, basically. So what I'm trying to say is that you can measure the behavior at P instead of relying on another second point. So you will not use the slope, but you will do the slope of the tangent line at a point. So now you can figure out what happened, what was the change of the function at that given point, only using one point, which is useful because in real life you don't always have 2 points. You don't always have so much information ready for you. You only have one minimum, or sometimes not even none. But that's for another topic. So what we want to know is the slope of the tangent line at P. So what does this mean? This means that if f is continuous, we can take the limit of the function to figure it out. This is the slope of the tangent line at P. So what does this mean? As x approaches A, so as Q comes closer to P, we get the limit, which is the instantaneous function, the instantaneous rate of change of the function at P. Because this will come closer to 0 because we're coming near, and this is the difference. So let's say this is 10 and this is 5. Minus 5 will be 5. But if x is 9, then it will be 4, then 3, so minus 5, 4. Then 8 minus 5, 3, until getting to almost 0, but it can never be 0. We can just approximate it. That's the purpose of a limit, to approximate a function, to approximate a value and see the behavior of it. So see this new function. As you can see, something changed, right? What happened? Well, let me just recall here. H equals the difference here, while x equals, okay, so we're just substituting here. All we did was substitute h for, sorry, substitute x minus a for h, and x here for h plus a, so it gets more easy. So you can see x goes here, but we're using this definition, and x minus a goes here, but we're using this definition. So that, as you can see here, we are just watching one point, which is what we wanted, right? We wanted to know the slope of a tangent line for one specific point, which we have it here. So let's do this in practice so it gets clear. Okay, so let's imagine a physics example. Let's imagine you have a balloon, right? One of those balloons that people go into, which I don't know why. Seems kind of boring. But anyway, let's say this balloon is 512 feet from the ground. And let's say that a bag, because as you might know, the way these balloons elevate, it's by dropping bags of sand, bags of sand or whatever. So let's say this balloon wants to go up and they drop a bag. Okay, that seems like something else. They drop a bag, and the position function of that bag is that's the position function. And by position function, I mean so this position function is used to determine the velocity of that bag at a given time. This is yt. So we want to know the velocity at how that bag was falling from the balloon at a time t. Using our function of the slope of a tangent line of a function, we have okay, so that means the function of a plus h minus the function of a over h, while h approaches 0. Why 0? Because it gets closer. Remember, point Q gets closer to point P. So let's do it. Cancel whatever we want, leaving us with, and we're using arithmetic here. So here, this is one crucial step. Here we cannot divide by 0, right? As you can see, if we plug in the limit here, if we approach the limit, the denominator will be 0, that's what we don't want. So if we factor h from the numerator, we get the following number. Which means that we can cancel this, and finally we obtain that the limit as h approaches 0, 32a. So now if we approach the limit, we get minus 32a. So that's our velocity. That's the velocity of the bag at time A, equals minus 32a. So why is the velocity at time A negative? Well, because the negative number indicates the velocity of the bag going downward on L, and L is this line. So going downward, downward, downward. Imagine this is a plane. It's going downward, downward, downward. That's why it's minus. It's going down. So what about the velocity of the bag at time of 2 seconds? So after 2 seconds, what is the velocity of the bag after it's dropped? Well, we would just plug 2 here. Seconds. Feet. Why feet? Because this distance is in feet. So okay, why did I plug in 2 here? Well, because instead of plugging in here 2, which I mean you can, but it would just be longer, you already have the function here at time A, and that time A can be anything, 1,000 minus 2,000,000, 2, 1. So you just plug in the time that you want. This is what exactly you're looking for, a function like that. So you can just plug in numbers, so you can use guess and use intuition to figure out what you're looking for. So the moment the bag hits the floor, how will you figure out that? So we know that, so this is a position function, right? We know that the position function equals 0 at the moment it hits the floor, because it's not longer moving, it's no longer going downwards, it's just stopped. So the position function, so the position is stable, that's 0. It doesn't move, it doesn't go up, it doesn't go down, it's just on the floor, death. That means that the position function equals 0. So 0 is the position function, which is basically the same as saying 0 s of t, which is a position function. That's the same as this. We're just deleting this part. It's saying that that was the moment that the bag hit the floor. So now we solve for t. Why? Because we want to know first at what time we will know at what time in seconds the bag hit the floor, and then we will know the velocity at that time. So first let's get t. 5.7 seconds. So at 5, we know that our prior example at 14 wasn't logical, because the bag hit the floor at 5.7 seconds. What was the velocity of it though? We will plug 5.7 seconds in our initial minus 32a, which equals 81 feet per second. So the bag, when it hit the floor, was going at 181 feet per second, and the bag hit the floor at 5.7 seconds. And this is why it's so crucial to know the slope of a tangent line, because you can figure out the position function, which is the most important thing. And by position I mean the position of anything. Like I said, the growth of bacteria, the total revenue of a company, the total quantity of a material, the velocity of a spaceship, anything can have the position, or the revenue. I mean the quantity. Position is just a noun I'm using, but you can use multiple nouns. You can use, instead of position, you can use quantity, you can use velocity, you can use anything. It depends on your background. And what we're looking for in the slope of a tangent line is the velocity, the behavior at that point. So you just have one input to plug in. For example, in this case was A. Now you're just looking for A, which is the time in this case. But like we said, it can be quantities, it can be revenue, it can be anything. This is the importance of the slope of a tangent line in calculus.